We're going to continue on the sturgeon theme. Rebecca Cohen from the Cornell Lab of Ornithology is with us. So thank you for being here.
Hi all. Thanks so much for having me here today. I'm representing a group of collaborators from a number of just different institutions, Cornell, the West Point Military Academy, SUNY, Brooklyn College, and then the Department of Environmental Conservation and the Hudson River National Estuarine Research Reserve. And I'm going to tell you today a little bit about some kind of fundamental legwork that we're doing in hopes of using passive acoustic monitoring to keep track of Atlantic sturgeon in the Hudson River coast. So Atlantic sturgeon are an anadromous species, and they range from Labrador down to the middle of Florida. And they historically spawn in all 38 major river systems of this region. And accounts of their abundance and their suitability for harvest range back to the colonial times. One such account from 1675 mentions that they were, quote, in some rivers so numerous that it is hazardous for canoes and the like small vessels. So because of their accessibility and their abundance, they were subject to highly intensive fishing pressure for hundreds of years until their populations completely crashed in the late 1800s. As is very similar with the lake sturgeon, these are very slow-growing animals. Females don't reach sexual maturity until between 15 and 30 years, and their interspawning interval is about 2 to 5 years. So they just couldn't withstand this kind of fishing pressure. Currently, they're managed as 5 distinct population segments. 4 of those population segments are listed as endangered as of 2012, and the 5th is threatened. And the largest population segment spawns in the Hudson River estuary. And like the rest of their range, this is a highly anthropized region. So threats to these animals include changes to habitat structure, invasive species, climate change, noise, shipping, etc. In the Hudson River, ovulatory and pre-ovulatory females have been observed only north of river kilometer 136, which is right around here. This is from Van Enen et al. 1996. So they sampled further down the river as well, but it was only between kilometers 136 and 182 that they found females who were actually in reproductive condition. And the thought is that the eggs, embryo, and larva are quite salt intolerant, and so spawning needs to occur above the tidal salt front, which is about kilometer 98, far enough above that as the embryos drift downstream, they have kind of a buffer of fresh water before they start hitting water with some salinity in it. The spawning aggregation rate here at Hyde Park has been the subject of quite intensive study by the DEC, which includes gill netting, telemetry tagging, egg mats, side scan sonar. But there's still a lot that we just don't know about these species and how they interact with habitat variables or with human activity. And a lot of these current approaches, and I'm sure you're all quite aware of, are really intensive in fieldwork and labor and time. And so our question was, can we monitor Atlantic sturgeon using an approach that is less intensive with fieldwork and effort, and also perhaps less invasive to these species? Catching and handling fish and injecting tags is sometimes suboptimal when you have an endangered species or one that is very sensitive to disturbance, right? So that's where passive acoustic monitoring comes in. If you're not familiar, what this entails is literally going out and putting a recording device in the environment, a hydrophone in this case, to passively record ambient soundscapes, and then identifying the cues of interest of the species that you're trying to study, whether those are intentionally produced cues, or sometimes they're just incidental sounds that are consistently associated with that species. This is really great for species which produce some kind of sound, but are hard to get eyes on either because they're inaccessible or which are sensitive to disturbance. A couple of the advantages of this approach is that field effort tends to be pretty minimal. You need to go out and deploy your devices, and then they can sit out there for sometimes quite long periods of time, sometimes 6 months, sometimes a year, and then you need to go retrieve them again. So it's, a little bit of effort on either end, but then you can get quite a long record of data. And so this has become quite widely adopted in the marine realm for monitoring of marine mammals, which is what my background was in, but also for fish and invertebrates. It's only really beginning to be adopted in freshwater settings, so I know that there's one more talk in this session later on about PAM and freshwater. Active sound production has been documented in about 1,000 fish species, but most species are still uncharacterized acoustically, but a recent phylogenetic work suggests that sound production is likely to be quite widespread in ray-finned fishes. And for a little bit of context, the work that I'm presenting here today is part of a larger project aimed at using passive acoustic surveys to monitor protected and invasive fish species in the Hudson River estuary system. You can see the monitoring sites that we're working in right here, which are aligned with the Herner component sites. Atlantic sturgeon were identified as a priority species for this project, but sound production has not been documented in Atlantic sturgeon. So that's where we're starting from, right? Sound production has been documented in lake sturgeon, also in pallid and shovel-nosed sturgeon, and there's also one like meeting abstract talking about sound production in a few Russian species, but it's really just the lake sturgeon that we have a good sense of. But closely related species can kind of serve as a starting point when we're looking for an acoustic cue associated with a new species who we'd like to monitor. Most work on lake sturgeon, most of the work has been done on lake sturgeon, and it consistently reports this kind of drumming or thundering sound. Rook and Binkowski in 2002 observed that the pulses in the drum coincide with thrashes of the male's tail as he swims up alongside the female and reduces his milt. But the exact mechanism of sound production isn't well understood. The best guess right now is that body muscle contractions end up vibrating the swim bladder and creating this resonance. Best guess. What you're looking at here are some visualizations of sturgeon thunder. This is from Higgs and Beach up on top here. On the left side here is a power spectrum. So we have frequency on the x-axis, which is tiny, and amplitude on the y-axis. So we're just looking at the distribution of energy across the frequency band. The top line shows the sturgeon thunder, and the bottom line is just ambient noise to give you a sense of like the background noise conditions. The right side is called a spectrogram, another visualization of sound data. Now we have the evolution of sound energy over a frequency band and over time. So on the y-axis is now time, on the x-axis is frequency. I just said it backwards. And then intensity of color gives the amplitude of the sound. So we can see that there's kind of a strong onset here, and then it fades out a little bit. On the bottom here, this is data which was shared with me directly by Dennis Higgs from the University of Windsor. We have the sound pressure time series on the top, which is literally just amplitude fluctuations in sound pressure over time, and on the bottom is another spectrogram, just in sound, in color rather. And I will try to play it, and let's see. Oh, that was the maximum sound. I'll try it.
Try again. Try turning that.
Oh, we'll try this. Yeah.
Try turning the TV up.
Oh, geez.
Sorry.
Now we're gonna hear.
All right,
thunder.
watch out now. Start over. Go back and do it. Okay, this is my last try. Sorry. There's a lot of fun on a later slide. We'll try it again. Okay, so thanks to the work of some of our